So far we have seen the Metropolis-Hastings algorithm, and we have seen how it works on a proposal distribution that is adaptive, that can cover the whole space of the target distribution. But we haven't answered what's the connection between the Markov chains and the MCMC algorithm, and what actually makes the Metropolis-Hastings algorithm work. So before we talk about how the Metropolis-Hastings algorithm works, we have to define what is a Markov chain. And actually, the Markov chain, we have already seen it in the previous lecture where we talk about the hidden Markov model. And this is simply given by the graphical model as shown in this diagram over here. So this is a first order Markov chain. And it is intuitive to introduce this Markov chains as in the finite state space, where x can take as discrete values. That means that I have a random variable of x. It can take any s number of discrete values, any one of this, one out of the s number of states. And the stochastic process is called Markov chain. We saw in the previous lecture that if the probability of the random variable, which we denote as xi, conditioned upon all the other random variables, is equal to the probability of xi conditioned upon x, which is the random variable in the previous time step, which we denote as xi minus 1 over here. So in this case here, it would be a S by S matrix, as we have seen in the previous lecture, where all the rows will sum up to 1. And here's the graphical model or the Bayesian network of this first order Markov chain, where we can see that any random variable here, xi, is conditionally independent of all the other random variables given the previous random variable. And this is can be seen by because the fact that this is a head-to-tail graphical model over here. Once we observe xi minus 1, all the rest of the states here, all the rest of the random variables becomes de-separated from the random variable of xi. Hence, it's sufficient to write this conditional probability as the probability of xi conditioned upon xi minus 1, which is the random variable in the previous time step. Here are some properties of the Markov chain which will allow us to derive the Metropolis-Hastings algorithm. The first property that we will look at is the homogeneous chain. We say that the Markov chain is homogeneous if the transition probability, this particular probability of xi conditioned upon xi minus 1, remains the same for any I. This means that in our Markov chain over here, regardless of the random variable that I'm looking at, x1, x2, x3 or x4 over here, the probability of x4 conditioned upon x3 is going to be the same as the probability of x3 conditioned upon x2, and so on and so forth. So this is given by T over here, which is what we have seen in the previous lecture as the transition matrix. And it will stay the same, which means that it's time invariant, and we call this a homogeneous chain or homogeneous Markov chain. And the second property that we are looking at for the Markov chain is that it must be a stationary and limiting distributions. And we say that a Markov chain is stationary and limiting when the probability vector of a certain state, this means that I'm looking at the marginal probability of x over here, which we denote as pi, since in this example we say that this is x is a random variable that takes 1 out of k or 1 out of s states over here. And this means that pi is actually a categorical distribution given by we can represent this using a vector of s numbers over here, where each one of these simply represents the multimodal distribution or the categorical distribution shown in this graph or histogram over here. And we say that the probability of x at any time, when it transits from one state to another state, it becomes the same probability when it transits from one time step to another time step. This means that the probability vector defined on x is a stationary distribution if this particular condition is fulfilled. This means that we are going to transit the current probability into the next step, and it still ends up to be the same probability distribution or probability vector on the random variable. And what's interesting here is that we can see that since T here is a S by S matrix, this particular equation here should remind you of this equation of x A transpose of equals to x over here, where it's actually the eigenvalue or eigenvector equation in linear algebra. So this means that x over here is actually our eigenvector that corresponds to the value where the eigenvalue lambda over here equals to 1. And we also say that pi over here is a limiting distribution where such that regardless of whatever state that we start with, suppose that we start with pi of 0, pi of 0 could be different from pi over here, the distribution, the vector of S numbers over here, it could be different. So as we move on, suppose that we start off from pi 0 multiplied by t, and this is going to give us pi 1. And then in the next step, we are going to compute pi 2 equals to pi 1 multiplied by t, and pi 3 is going to be equals to pi 2 multiplied by t, and so on and so forth. There will be, it will come to a certain stage where we see that no matter how many times we multiply by t, we are always going to get the same pi. This means that we have convergence to a limiting distribution, and this would be also known as the stationary distribution. An example of the transition graph of a Markov chain with the three random variables x1, x2, and x3 over here. We can verify for ourselves that if t here is a valid transition matrix that denotes the transition probability of xi condition upon xi minus 1, then what we can do here is that starting from any initial state that of the probability of x, suppose that we start off from 0.5, 0.2, and 0.3, note that the sum of all these values must sum up to 1. It must sum up to 1 because this is a categorical distribution. So we'll start off with this vector, the random vector over here, and then we'll start to transit using the this particular transition matrix over here by post multiplying the t with my random vector, and after the first step I will get this value over here if we take this multiplied by this matrix over here, and eventually it will come to a stage where after multiplying t, I will get the same number over and over again. So no matter how many times I'm multiplying by t, mu multiplied by t, I'm always going to get this same set of vector. And this is where we say that it has already convergence to a stationary distribution, or we simply say that this vector over here is our limiting distribution. So another property of the Markov chain is what we call the irreducibility property. And we say that a Markov chain is irreducible if for any state of the Markov chain there is a positive probability of visiting all the other states. So what this means in terms of the transition diagram, suppose that each random variable takes 3 states. This means that I have a transition diagram that looks something like this, where k equals to 1, k equals to 2, and k equals to 3. Well, what this means is that if I start off at any particular state, there must be a positive probability that I can move to any other states in the state space. And what this simply means is that the transition probability here, none of this can be 0. Otherwise, I might get stuck in a particular state of the random variable. So all this probability, if I start off with the state of x equals to 3, it must be able to, there must be a positive probability for me to transit to k equals to 1 or k equals to 2. And we simply write this that for any state of a and b that is in the state space, for any time step that is more than or equals to 0, the probability that x at time t going to take a state of b, conditioned upon that it has started off with a state of a, must be more than 0. This means that any state that I start off with, I must be able to transit to any state of b. Another property of the Markov chain is what we call the aperiodicity, and this means that the Markov chain should not get trapped in any cycles. So what this means is that the number of the states that we are in for any random variable should not be cyclical. It should not occur in a periodic manner. And what this means is that suppose that I have this Markov chain, for example, and in this case, let's say if I have where x can take any state of a, b, and c. Now suppose that if I were to start off with the first random variable of x1 over here, and this is going to take a state of a, and if I were to transit over x2, x3, and it happens that in x3 it's also a again, and then subsequently in x4 and x5 this is also going to take a state of a again. So what this means is that there is a periodic cycle where the state of a is always going to occur at every other third random variable in the Markov chain. Then we say that in this case here, the Markov chain gets trapped in a particular cycle. And what it means here is that the probability that we start off with a, where the random variable, the first random variable x0 taking a state of a, and at the time step of t equals to where xt equals to a, this means that the same state occur again after a certain time step of t. The probability of this occurring more than 0 should not be in a regular cycle, which we compute using the greatest common divisor, and this greater common divisor must be equals to 1. Equals to 1 over here simply means that the chance of the same state occurring must be equivalent for every random variable at any time step over all the states that x can take. And we say that a Markov chain is ergodic if it is both irreducible as well as aperiodic. So ergodicity is very important. It simply implies that we can reach the stationary or limiting distribution pi no matter what we initiate the initial distribution of pi 0 to be. And so in order, we'll see that in the next few slides, we'll see that that all the good MCMC algorithms must satisfy ergodicity so that we can initialize with any state of the random variable. That means that we can initialize any samples to take any states, and then we are still guaranteed that the sampling will converge to the samples from the target distribution. Now let us define the detailed balance in order to prove the Metropolis-Hastings algorithm, or to show that the Metropolis-Hastings algorithm actually works. The detailed balance is also otherwise known as the reversibility. So suppose that we start off with a probability vector pi equals to p of x defined on the state space of x, and it satisfies the detailed balance with respect to t if this particular equation over here, the condition over here, is valid. So what this means is that it can be reversed. It means that from A, if I transit it to B using the transition matrix here, the transpose of this transition matrix applied on B should get me back to A. And the first remark that I'm going to make here is that the detailed balance implies that stationary distribution is fulfilled. So here's the proof, where we start off from computing the marginal probability of pi b, which is given by the marginalization over a over the left hand side of this equation over here. And we can see that in this case here, the sum can be pushed into the product terms over here, where we simply replace this term over here by the right hand side of the detail balance equation over here, and then we can push the summation inside here. And here we can see that the summation of over t, since the sum over all the columns over here are going to be or the rows over here are going to be equals to 1, we end up to get a pi of b, where this guy over here is simply our transition matrix. And we can see that by transiting b, we, no matter how many times we transit, since the transition matrix now equals to 1, this means that we always end up to be the same distribution, and hence the stationary distribution is satisfied. And since we derive this equation over here, this stationary distribution relation over here from the detail balance, what it also implies is that stationary distribution implies this detail balance, or a detail balance also implies the stationary distribution. The second remark is that detail balance implies reversibility. So this is just a terminology where is used to describe what I have described earlier on, that starting from any state of probability of pi a, after applying the transition matrix, I will be able to get to the next state, which is pi b. But applying pi b on the transition transpose of the transition matrix, which is t of ba, I'll be also able to get back to the original probability distribution of pi a, which is given earlier. Now, we'll put all these definitions of the detail balance as well as the properties of the Markov chain together to show why does the Metropolis-Hastings algorithm works, and what's even more fascinating is that why does the simple algorithm, such a simple algorithm of Metropolis-Hastings algorithm, turns out to be such a powerful and always guaranteed to converge algorithm. So recall that we draw a sample of x prime according to the proposal distribution, adaptive proposal distribution given by q of x prime condition upon x. And then we will accept or reject according to the acceptance probability or acceptance condition over here given by a, x prime, and x. So in other words, the transition kernel is given by t equals to q multiplied by a over here. And we shall use this to prove that the Metropolis-Hastings algorithm satisfies the detail balance, which means that it will converge to a stationary distribution that is equivalent to our target distribution. So recall that the acceptance condition is given by this equation over here, where we take the mean of 1 or the ratio that is computed from this, the target, a normalized target distribution, as well as the proposal distribution. So notice that the acceptance criteria here implies the following. If the acceptance criteria is lesser or equals to 1, then this means that the inverse of this particular condition over here is more than or equals to 1. This means that because it's more than or equals to 1, this means that the inverse of this is going to be less than or equals to 1, which we choose the mean of it, which we are going to choose this particular condition, which satisfy this criteria over here, that is going to be lesser or equals to 1. And thus, the acceptance criteria of the inverse of x and x prime is going to be equals to 1. This means that we are going to invert this and more than, which is more than 1, and we are going to rewrite this as x and x prime, and this is going to be equals to the mean of 1 and the inverse of this particular condition over here, which is equivalent, this particular term over here is equivalent to this term over here. So since it's more than 1, we are going to choose 1 over here. Now suppose that x prime and x is lesser than 1 and x and x prime equals to 1, which is what we have defined earlier. We have this acceptance criteria of x prime and x equals to this condition. This is what we have seen earlier in this particular slide over here. And now we're going to start off from this definition over here, where we are going to bring the denominator here across to the other side. So and we'll end up with this particular expression over here. And we are going to introduce ax and x prime equals to 1 into the relation over here. Since ax and x prime is equals to 1, we'll simply multiply this term over here by 1 to get this term over here. And now what's interesting is that we can collectively write a and q over here as our transition kernel, pre-multiplying it by our unnormalized probability vector over here. And on the right hand side of the equation, we can do the same thing. We can collectively call a and q, the multiplication of these two, to be our transition kernel, and pre-multiplying it with our unnormalized target distribution of x prime, where x prime represents the current sample and x represents our previous sample. And this is exactly the detail balance condition, where we simply write the unnormalized probability of x as pi of a, and this guy over here, the transition probability, as TAB, which brings us from the current state to the next state. And this is equals to pi of b multiplied by b of a. And this is exactly what we've seen earlier as the detail balance condition. So in other words, the Metropolis-Hastings algorithm actually leads to a stationary distribution. This means that as we sample more and more, or increasingly number of samples, eventually we will converge to this stationary distribution, which is given by our unnormalized target distribution. And that's exactly the distribution that we want to draw sample from. And thus, the Metropolis-Hastings algorithm eventually converges to the true distribution given by P of x. There's also a special case of the Metropolis-Hastings algorithm, which we note as the Metropolis algorithm. This is a special case where the proposal distribution is a random walk. This means that the proposal distribution is a symmetrical distribution. An example is that it is an isotropic Gaussian distribution. What this means is that the covariance of this particular Gaussian distribution is identical, diagonal and identical. This means that if we plot out a two-dimensional isotropic Gaussian distribution of x1 and x2, we'll see that it's actually a circle. What this means is that starting from this particular location here, we will end up to be anywhere on this particular distribution. We will have an equal chance of getting to anywhere. Hence the word of a random walk. We are walking randomly in the state space. And as a result, the acceptance probability of the Metropolis-Hastings algorithm is now given by this equation over here, where since we say that the proposal distribution is symmetrical, this means that the numerator term over here and the denominator term cancels off, and we'll end up with the acceptance condition to be the mean of 1 and p tilde x prime divided by p tilde of x. Here's an illustration of using the Metropolis algorithm where the proposal distribution is actually a isotropic Gaussian to sample from a Gaussian distribution. So here we see that there are rejected samples over here, where these are the paths. This is actually the paths of the acceptance of the samples that is drawn, and the green line represents the accepted samples, which you can see that they fall under this Gaussian distribution over here, and the red ones are the samples that are rejected from the sampling. Now the last algorithm that we're going to talk about is the Gibbs sampling algorithm. It's also a special case of the Metropolis-Hastings algorithm, where we can write the target distribution, which consists of the joint random variable or joint probability distribution of x1 all the way to xn. We suppose that we can write for any random variable denoted by xj over here, we can write the conditional probabilities, the full conditional probability of any random variable xj in this particular set, conditioned upon all the other random variables except for the random variable of xj itself. So in this case here, we can use, if we are able to write this conditional distribution for all the random variables, we can apply the Gibbs sampling algorithm, which is a special case of the Metropolis-Hastings algorithm. And in this case, we'll use the following proposal distribution for all the random variables. And here we'll sample every random variable one by one, where we'll not sample everything as a set, in contrast to what we have seen earlier on. So in this case here, we'll simply let the proposal distribution Q of x prime conditional upon xi, which is the previous sample, to be equals to the conditional probability of xj conditioned upon all the other random variables in the graphical model except for xj itself, or otherwise 0 here. Now we can see that Gibbs sampling is a special case of the Metropolis-Hastings algorithm, where the acceptance probability is always 1. This means that we don't have to evaluate this particular step in our Gibbs sampling algorithm, in contrast to the Metropolis-Hastings algorithm. Here's the proof of why is it always equals to 1, starting from the acceptance condition, which is given by this expression over here, where now the target distribution here, x, is always going to be written in a full conditional form, which we have seen earlier. And here x equals to this equation over here, where it's equals to xj conditioned upon everything except for xj, where x prime here equals to the probability of xj prime condition upon x prime of all the other random variable except for j itself. And plugging these terms into these conditions over here, we will get this particular expression over here. And since that x prime of all the other random variable except for j itself is going to be equals to x of all the other random variable except for j of the previous step, this means that we are going to hold the states of this xj or x of all the other random variable, or x of all the other random variable except for j itself, to be constant, to be held fixed during the sampling step of xj. We'll see that by substituting these terms into this equation over here, this particular part over here can be cancelled out. We'll see that this cancels off, as well as this cancels off. This means that the acceptance probability will always be equals to 1, which means that we'll always accept all the samples. And here's a summary of the Gibbs sampling algorithm. It's also a very simple algorithm, yet it's very powerful. It always works very well. We'll first initialize all the random variables xi, where I equals to 1 to m, the m number of random variables, to a certain random states. And then we'll sample t number of times, where we'll generate all these samples, t number of samples for x1 all the way to xm over here. The first step here would be we'll first select the sample of x1, and we'll draw this particular sample from the conditional probability as the proposal distribution, as what we have defined earlier. So here, since we are sampling x1, we'll sample from the conditional probability of x1 conditioned upon all the other random variables, conditioned upon that they are observed at a certain state of the initialization here. And we will simply evaluate this and draw a sample from here. So and then once we get the sample of x1, we will put this x1, the state that we have sampled from x1 over here, to the conditions of the second sample, of the second proposal distribution that we use to draw x2. So here x2 will be conditioned upon x1 at the state where we have drawn in the previous step, and all the others will remain the same. And then subsequently we'll do the same for all the other random variables one by one. When after we have sampled, draw a sample of that particular random variable, we'll put it back into the conditional probability distribution so that we can use it as a proposal distribution to sample the next sample until we are finally done with the whole set. And this would be our tau plus 1 set of sample for the set of random variables, and we'll iterate this until we finally have t number of sets of the total sample for all the random variables. At first sight, the conditional probability of xj condition upon all the other random variables except for itself looks intimidating, but actually it's not that difficult to compute this particular conditional probability, because let's recall the Markov blankets. What it means here is that this particular conditional probability is only conditioned upon the Markov blanket of xj, where all the other irrelevant random variables, they are separated once the Markov blanket has been observed. So in the terms of the Bayesian network, this would be the parents, co-parents, and the children of the random variable of xj. And in the case of a random field, it will be easy. This is directly the immediate neighbors of the random variable of xj according to the Markov property. Finally, let's look at one example on how to do Gibbs sampling on a Bayesian network. Suppose that we are given this Bayesian network that consists of 5 random variables, and all the probability distribution tables that is given to us, which will allow us to write the joint probability distribution of A, B, E, and J and M to be equals to the probability of B multiplied by the probability of E multiplied by the probability of A conditional upon B and E, as well as the probability of J conditional upon A and probability of M conditional upon A. So we are given all this distribution. Now let's start to do the Gibbs sampling, and we'll initialize all the random variables at time step equals to 0 to false over here, where each one of these random variable is simply a binary state. That means that it takes either true or a false state, and we'll initialize everything to false. So the first step that we will do is that we will draw a sample of B from the conditional probability of so it should be the conditional probability of all B conditioned upon all the other random variables except for itself, which means that we are going to condition B upon A, E, J, and M. But this is equals to the conditional probability of B conditioned upon the Markov blanket. Since this is a Bayesian network, this means that B is only dependent on the children, the co-children, the co-parents, as well as the parents of the random variable itself. So in this case, we have a children, which is A, and we have a co-parent, which is E, and we'll write this conditional probability as the probability of B conditional upon A and E. And this is proportion to these two terms over here using the Bayes rule. So we can see that we can evaluate these two terms over here, the probability of these two terms over here, using the existing condition of A and E. So what this means is that A and E here, since they are both false, they are initialized to false, what we are interested would be to compute the probability of PB conditioned upon A equals to false as well as E equals to false over here. And what we want to do is that we want to draw a sample of B from this particular probability distribution, which we can further evaluate using the Bayes rule. And now, since B takes a binary state, we can easily compute these two probabilities from the given probability distribution tables that works out to be these two values over here. And of course, we need to normalize these two such that they sum to 1. And the next thing that we'll do is to simply draw a sample from the uniform distribution that is between 0 and 1. And then we will check that if this number is more than this probability over here after the normalization, then we will let B take a state of false. And if it is less than that, we will we'll assign B to take a state of true. So in this case, suppose that this number, the random number that we draw, is more than this number over here, then we will assign it as a state of false. The next thing that we will do is to draw a sample of E from the conditional probability of P of E condition upon all the other random variable except for E itself. So it will be B, A, J, and M. And here we will use the Markov blanket as well of E, which is the child, and the co-parent, which is B and A. And this is why we get this particular probability distribution over here. And that's proportional to this guy over here using the Bayes rule. We'll do the same thing, evaluate this probability since it's two state, true or false, and then we'll draw a random number from the uniform distribution between 0 and 1, and then we will check this number. If it is more than this number over here, then we will let E be false, and if it is less than, we will let E be true. Suppose that it's less than, we will let E be true. Now we repeat this for all the other random variable, the remaining random variable. So it will be A that we need to draw from this conditional probability. We'll do the same thing, compute this using the Bayes rule, and then draw a random number from a uniform distribution and check if it is more than or greater than this particular, or less than this particular number over here. And we'll fill in the this state over here. And we'll do this eventually until we fill up the whole table over here. So now another thing to note is that in this example, I say that all the random variables here are only two states. That means that they take only true or false, and hence it's sufficient to draw a random number from the uniform distribution of 0 to 1, and we'll simply check this whether it's bigger or smaller than one of the particular probability values that denotes B. Suppose B equals to true or B equals to false over here. But in the case where, let's say, our random variable takes three states, 0, 1, or 2, then the way that we draw the random sample from this probability distribution, so we will have three probability distribution over here: B equals to 0 condition upon something, B equals to 1 condition upon something, and B equals to 2 condition upon something. So we'll be able to compute these three values over here, V1, V2, and V3. And the way that we draw sample from this would be that we'll still draw a sample, random sample from the uniform distribution between 0 to 1. And since V1, V2, and V3 adds up to be 1, we will check that whether U over here, this random sample over here, overlaps whichever range over here. So we can think of this as a roulette wheel, where we simply divide this roulette wheel into three slices over here, where we call it V1, this probability, which is proportional to the probability of V1, V2, and V3. So suppose that this is the 0 point, and then the value gradually increase all the way to 1 over here. And we'll draw a sample of U that is within 0 and 1, and we'll see whether U falls into any of these regions. Suppose that it falls into this region over here, then we will let B, the sample of B, take the state of 3. Now, here's an illustration of the Gibbs sampling algorithm. It's similar to the block coordinate descent optimization algorithm, where in this case, we only have two random variables, which is x1 and x2 over here. So when we are sampling for x1, we'll hold x2 constant, and we'll move along the axis of x1, where x2 is held constant at this particular value here. And when we sample for x2, we'll hold x1 constant, and this is the direction that we'll move. So we'll continue to move in this octagonal direction to the axis, while we draw sample from the target distribution until we are done with the number of samples. And in summary, we have looked at how to use the Monte Carlo principle to justify for the sampling algorithms. And we have looked at various sampling algorithms such as the rejection importance, Metropolis-Hastings, Metropolis and Gibbs sampling algorithm, to allow us to compute the maximum probability, approximate inference, as well as expectation. And we also look at the Markov chain property that allow us to explain the validity of the Metropolis-Hastings algorithm. Thank you.